Swayam Prabha. Digital India. Educated India.
Lecture of this course, Fundamentals and Applications of Dielectric Ceramics. So, in the previous few lectures we looked at the structure formation of these dielectric ceramics. So, basically most of the dielectric ceramics are based on ionic bonding of cations and anions. As a result, they follow what we call as Pauling's rules, and which are essentially based on formation of polyhedras by anions being bigger ions and cations occupying the interstices between them depending upon the radius ratios. So, we looked at essentially FCC based structures, the cubic based structures, and HCP packed structures, which are the most common ones. There are other structures as well, but these are the most common structures that we looked at in the last few lectures. So, now we move on to the a new topic here, which is essentially based, which is important from the perspective of properties. So, here we are going to look at what we call as the defect chemistry of basically oxides. So, because many dielectric materials tend to be oxides in terms of their chemistry, defect chemistry plays a very important role, because what is defect chemistry is basically most of these materials, whether you have AO or A2O3, variety of these materials, they tend to carry defects which are not. So, here we are not talking of defects like dislocations and grain boundaries and surfaces. Here we are going to talk about the defects which are mainly point defects. So, defects basically which are 0 dimensional defects or point defects. So, these defects are very important, because these defects, when they are present in them, they change the dielectrical properties. And these electrical properties essentially are modified, especially the conductivity, the electrical conductivity changes quite extensively, and this has very important ramification on the use of these materials, and this is affected by chemistry, the environment in which they are used, the chemical reactions, and variety of other things. In this few lectures, in next few lectures, we will look at a few fundamental aspects of defect chemistry of these materials, which can enable you to tailor the properties when you work on them as a part of your research or industry or wherever you are. So, the books that we are going to follow, I told you the books earlier, but the books that we are going to follow basically, if you look at physical ceramics, by Y.M. Chiang, D.P. and W.D. Kingeri. So, this has a chapter on defect chemistry, and then if you are interested in deeper aspects, then you can look at non-stoichiometry, diffusion, and electrical conductivity in binary metal oxides by Per-Kofstad, Per-Kofstad. Okay. So, these are the two books that you can look at. Ceramics will fulfill the criteria for this course, this physical ceramics book, but if you wanted to get into details, you can go through this non-stoichiometry, diffusion, electrical conductivity by Per-Kofstad. So, what are these? Now, let us begin our discussion with what these defects are. So, we first begin with what we call as point defects. And these point defects are basically caused by deviations from perfect atomic, you can say arrangement or stoichiometry. Okay. So these could be missing ions, these could be interstitial ions, these could be substitutional atoms, and these could be presence of extra electrons or holes, these kind of things. Usually these point defects are electrically neutral in metals, but in oxides they are charged and they change the electrical properties quite significantly. So what are these? So some of these defects are basically subcategorized into ionic defects. Ionic defects are basically the defects which occupy lattice positions or interstitial sites. These could be, so examples are vacancies, interstitials, both host or impurity, substitutional ions, so these are again substitutional ions can be basically impurity atoms, and it could be anti-site defects, anti-site atoms or ions. Okay. So these are some examples of ionic defects. The electronic defects on the other hand are basically they are because of deviations from the ground state. So basically when you have excitation of electrons or holes, so you form electrons, extra electrons or holes in the system. Okay. And these are determined as these are depicted as E or H. Okay. So basically when you have deviations from the ground state, you have excitations. For example, if you excite a electron from the valence to conduction band, this leads to creation of electron and a hole. You can also possibly, if you put in an impurity, if the impurity is different charge. So for example, we know in the case of silicon, right, in the case of silicon, when we put phosphorus in it, the silicon is +4, phosphorus is +5. What phosphorus does it creates extra electrons in the and this makes silicon n-type, and those n-type are extra electrons, right, extra charge that is created. These are electronic defects. Similarly, when you put in a 3+, like boron is 3+, right, it creates holes. So these are basically electronic defects as we call them. So before we go into details of this defect chemistry, let's first look at the notation. The notation is called as Kroger-Wink notation. So Kroger-Wink notation generally, in this case, let's say you have a metal oxide as MO. So M is the metal and O is the oxygen atom. Okay. So if you have metal on metal site, it's going to be MM. So this is regular metal site. Okay. Similarly, if you have an ion on regular anion site, it's going to be OO or XX. Okay. The defects are defects are depicted little differently. So if you have anion vacancy, which is basically oxygen vacancy in this case, in most cases, then this is going to be VO. Okay, and this could be a neutral vacancy, it could be a charged vacancy. So if it is a neutral vacancy, you write it as VOX. If it is charged vacancy, then you write it as VO dot or VO double dot. It can carry one positive charge or two positive charges. The oxygen vacancy is positively charged. So dot represents, in this case, positive charge. Okay. So it could be VOX, X will mean neutral, VO dot will mean single positive charge, and VO double dot will mean it's double positive charge. Similarly, a metal vacancy will mean, metal vacancy will be VM. Again, neutral would be VOX. If it is charged, then it would be VM dash. This will be one negative charge. And if it is doubly charged, it's VM double dash. If it's triply charged, it's VM triple dash. So for example, for Al3 plus, you can have up to VM triple dash. For zirconium, you can have VM 4 dash. For niobium, you may have VM 5 dash, because their valences are +3, +4 and +5. So that is how it will change depending upon the. So, and if you have metal interstitial, it will be Mi. Again, it could be MIX, it could be Mi dot, it could be Mi double dot, and so on and so forth, depending upon the valence of the metal, whether it's completely ionized or whether it's partially ionized or whether it's unionized. Unionized will mean it is MIX, it doesn't lead to any extra charges. Mi dot will mean it leads to extra charges. So if, for example, phosphorus and silicon was P, so it would be Pi or it would be P dot, okay, because it gives rise to, basically phosphorus atom is giving rise to one positive charge on the silicon site plus an extra electron. Okay, so this is how it becomes charge neutral, right. So if you put a metal, for example, inside a metal, so it may give rise to charges or it may not give rise to charges depending upon its ionization energy. So it depends. So this reaction, whether it will take place or not, it depends upon the ionization energy of the impurity. Similarly, you can have oxygen interstitial. This will be OI, and this OI can again be OIX, it can be OI dash, it could be OI double dash. In case of oxygen, it can maximum have OI double dash because oxygen has valence of -2. If you have a foreign cation, foreign cation is generally MF, and this MF can also take positive and negative charges depending upon where and how it goes. Okay, and there are some other conventions that we will see as we continue in the course. Okay, and generally electrons and holes are written as, electrons are depicted as E dash and holes are depicted as H dot. Okay. So these, wherever you have X, it means neutral, wherever you have dot or dash, it means charged. Okay. So this is basically the Kroger-Wink notation. So defects are usually represented by writing what we call as defect reactions. Okay, they are sort of chemical reactions. So but we need to follow certain rules, and the rules are, First one is that the ratio of cation to anion sites for the host lattice, right, as per the host lattice, is always constant. So, which is basically it is a law of site conservation. Okay. So, if it is AO lattice, which means number of A sites is equal to number of O sites, you cannot change that ratio. You cannot make it A2O3 or you cannot make it A2O. AO is the host lattice. Then mass balance. So, mass balance has to be preserved. You have to have mass balance. Whatever goes in has to be accommodated and accounted for. You cannot have changes, you cannot have disturbance in the masses, you cannot have inequality in the masses. You have to account for each and everything that comes in and goes out. And then we have electrical neutrality. In the end, to be preserved. So, mass balance has to be preserved, electrical neutrality has to be preserved, solid has to be always electrically neutral, you cannot have imbalance of charges. So, all the positive charges have to satisfy all the negative charges, so that solid is always electrically neutral. So, when you write defect reaction, these three rules are holy grail. You have to have site conservation, you have to have mass conservation, you have to have electrical neutrality condition to be fulfilled, and that is how we write. And when we write defect reactions, and generally from the perspective of teaching, we will assume complete ionization. So, in case of oxygen vacancies, it will be VO dot dot. In case of metal interstitial, let us say if it's 2 plus metal, then it will be Mi dot dot. In case of metal vacancy, it will be Vm dash dash. So, we are taking complete ionization instead of, there are possibilities you can have incomplete ionization in practice, but for the sake of teaching this module, we will consider complete ionization of all the defects. So, let us first consider defects in stoichiometric oxides. So, stoichiometric oxides are basically, when the defects form, they do not change the stoichiometry. Okay. So, if you have oxide MO, the stoichiometry remains as M is to O as 1:1. So, no matter what the defect forms, the number of metal ions, ratio of number of metal ions to number of oxygen ions remain always similar. So, in this case what might, so the defects which form in such scenarios, you can have cation and anion vacancies. You can also form cation slash anion vacancies and corresponding interstitials. Okay. You can have interchange of atoms, basically anti-site defects. You can have vacancies and misplaced atom of same kind of. So, you can have, for example, combination of metal vacancy and then you have metal sitting on oxygen site. There is a possibility. So, you have oxygen missing as well as there are various possibilities which, so you will have, sorry, Vm plus VO does not change the ratio. So, you have M:O, which is the same, okay, as parent. You can have Vm plus Mi. So, metal has left metal site and gone to interstitial site, which means M:O remains the, we have done nothing to oxygen and we have done nothing to metal, because metal ions are same in number. So, these are various possibilities, and we will see how these, there is a possibility that you can form interstitials also. So, you might have OI and Mi without forming any vacancies. You bring in extra oxygen, extra metal, both of them sit in the interstitial site without changing the stoichiometry. So, many combinations are possible. Let us see few of them how they exist. So, first of these stoichiometric defect is called as Schottky defect. So, the Schottky disorder is basically, you have, this defects is basically formation of cation and anion vacancies in stoichiometric ratio. Okay. So, if you have oxide MO, for MO, basically you can write this reaction as, you have one M and one O. So, you can say you had M at M site and O at O site. Okay. They go out of the system. So, you can say that this M and this O go, so M goes out and O go out. They create vacancies at the oxygen and metal site, right, VO and VM, and these vacancies will be negatively and these vacancies will be positively charged. So, this is basically, alternatively you can write this reaction as, so you have seen that this has not changed the stoichiometry. For each molecule of MO, one molecule has gone out, it has created one vacancy. So, you can write this reaction as 0 or null is equal to Vm plus VO. Okay. So, this generally happens. So, what this means is that both metal and oxygen have to leave the system. So, this generally does not happen in the interior of the system, it happens at the surface. That is why these defects are usually found, because the metals and oxygen have to diffuse out of the system, and this diffusion takes energy and it is more plausible at the surface than in the interior. So, these defects generally form at the surface. So, basically if you look at a structure, it looks like, so you have, let us say this is a lattice, let us say you have these as oxygen ions, and let us say you have these as metal ions, okay. So, right now this is all stoichiometric, right. Now, in the Schottky defect, what will happen is that this will become a vacancy. So, this will become, you can denote a vacancy like, so let us say this becomes a vacancy, this becomes V. So, this was metal, this was oxygen, let us say, okay. So, this becomes VO, and similarly this metal here, it will become VM. So, you have pair of vacancies without changing the stoichiometry. So, M is to O is fixed, okay. So, this is called a Schottky reaction, and this reaction generally happens at the outer or inner surfaces or at dislocations wherever energetics diffuses, permits it, and generally these metals and oxygen, they diffuse out of the system until you reach equilibrium. So, So, this is the equilibrium defect. You will have some of these defects always present thermodynamically in a system. We will do the thermodynamics later on. And these defects are generally preferred when anion and cation are of equal sizes or comparable sizes. So, this is for MO. Suppose you wanted to do it for Al2O3. For Al2O3 you can write a reaction as 0. So, here you can see the stoichiometry is 2:3. So, which means you will have 2 vacancies of aluminum plus 3 vacancies of oxygen. So, you can see you have site neutrality, you have mass neutrality, mass conservation, you have charge conservation, you have 6 of negative and 6 of positive charges. So, you can write this reaction for. So, this is called a stoichiometric defect. It does not change the stoichiometry of the system. And the materials which show this kind of defects are things like sodium chloride, magnesium oxide, Al2O3, TiO2, many of these materials show this kind of Schottky defects. Second defect in this series is called as Frenkel disorder. Frenkel disorder is basically about formation of, so if you have, it is about formation of metal interstitial and a vacancy. So, either metal or anion interstitial and a vacancy. So, the way this reaction is written as you have 0 Vm plus Mi or Vx plus Xi. So, let us say if X is doubly charged as well, then you will have Vx and Xi. So, you will form either metal interstitial or vacancy of metal and vacancy of metal, or you will form vacancy of anion and anion interstitial. In both cases, either this or that, in both cases the stoichiometry is not disturbed because metal has not gone out of system, it has remained inside the system. So, M is to X is same, it is preserved. Okay. So, mass is preserved. You can see there is a site preservation. You have not created any extra site because it has gone to interstitial site. Interstitial sites cannot be created or destroyed, and vacancy has been created on the metal site itself. So, this happens inside the crystal because nothing has to leave, and it happens only when cations. So, inside the crystal and then smaller, it happens in systems with smaller cations. So, things like AgI, AgBr, many halides show this kind of system where this kind of reaction. Okay. So, this is Frenkel or anti-Frenkel. So, in this case it is called as Frenkel in case of cation, anion, and anti-Frenkel in case, anti-Frenkel in case of anion and Frenkel in case of cation. So, we will stop here today. Remaining defect chemistry we will take up in the next lecture. Thank you.